So here you can see the partial molar quantities. So if you want to understand the partial molar quantities, that is the effect of change in the composition of the system on the thermodynamic properties of the system. So that means if one system, if there will be change in composition of any type of thermodynamic, any type of system, then what will happen to the thermodynamic properties, that will discuss in the partial molar properties, partial molar quantities or partial molar properties. As you know that the composition of the system comes into the picture only when the system consists more than one substance, because composition will be one variable. If the system contains more than one substance, that means if the system will be a mixture, when the substances do not react with each other, and we will call them the components of the system. A solution having one solvent and one solute has two components, and that is known as a binary solution. So when you dissolve sodium chloride in water, we get a binary solution in which sodium chloride is the solute and water is the solvent. And a solution having one solvent and two solutes, and if they do not react with one another, then the solution is called a ternary solution. And similarly, a solute and two immiscible solvents also make a ternary solution. The solute can be solid, liquid, or gaseous state. A solution formed by dissolving two solutes. For example, if you want to dissolve sodium chloride and potassium nitrate in water, so that is one example of ternary solution. In case both the components are liquid and the mixture is known as a solution only if both the liquids are completely miscible. So that means here we will change the composition, means the system should contains more than one component. So first if we consider a system with more than one component, suppose if we consider a binary solution, so then the concentration or then the strength of the binary solution can be expressed in different types of, by different modes. The first one is molarity. So it is defined as the number of moles of the solute dissolved per liter of the solution, or dissolved per decimeter cube of the solution. And the concentration component, the concentration of component I, here it is given as Ci equals to Ni into 1000 divided by V. So here V the volume of the solution in ml or centimeter cube, that is called Cc or ml, and Ni is the number of moles of the component of ith component, and hence the unit of molarity is moles per liter or moles per decimeter cube. And similarly, the another one is molality. So all the molarity is applicable for binary solution, and similarly the another one to express the strength of the solution, that is called molality, which is defined as amount of solute or the number of moles of solute per kilogram of solvent. And here the mathematical form of molality, Mi equals to Ni into 1000 divided by W. Here W is mass of the solvent in gram, and Ni is the number of moles of the ith component of the solute. So the unit of molality is mole per kg. It is important to note that contrary to molarity and molarity is not affected by change in temperature. Now coming to mole fraction. So this type of expression is used if you want to prepare a solution having more than two components, and also that is applicable for a two component solution. So here the mole fraction, that is chi I. So it is expressed as chi. The symbol of the mole fraction is chi, and in some book you can find that it is also expressed in x. So chi I, or the mole fraction of the ith component, equals to number of moles of the ith component divided by total number of moles of the solution, or total number of moles of the mixture. So if two components A and B having number of moles Na moles and Nb moles respectively form a solution or form a mixture, then the number of then the mole fraction of first component A, that is chi A, equals to number of moles of A Na divided by Na plus Nb. And similarly, the mole fraction of the second component, that is chi B, equals to number of moles of B Nb divided by total number of moles Na plus Nb. And if the solution will be a binary solution, and if we add the mole fraction of the two components, then the total value will become 1. So all these things you have studied. Now coming to partial molar properties. So this is the partial molar properties are extensive property of the system, because we know that extensive properties of a system depend on amount of the substance, and here partial molar properties are the extensive properties. If we divide such a properties by number of moles, then we will get the corresponding molar properties, that is properties per mole of the substance. For example, if we represent extensive thermodynamic properties, so in the lower classes we know that, so these are the extensive properties: volume, internal energy, volume V, internal energy U, enthalpy H, and Helmholtz function A, Gibbs function G, that we have discussed in the last class. So here, if we represent these extensive thermodynamic properties as X, then the partial molar properties Xm equals to X by N, that is the value of the thermodynamic properties of the system divided by number of moles, amount of the substance in moles. So here you may note that the molar properties are represented by suffixing M to the symbol of the property. That means if we put subscript M, then that will become molar property. For example, volume of 1 mole of the substance is known as molar volume, and that is represented as Vm, which is equals to total volume divided by total number of moles N. Now let us write the mathematical expression for change in thermodynamic properties X with change in composition of the system. Now we will discuss the partial molar properties. So let us write the mathematical expression for the change in thermodynamic properties X with change in composition of the system. For one component system, the extensive properties like internal energy, enthalpy, entropy, and Gibbs energy depend upon the temperature, pressure, and amount of the substance present. In fact, so these are extensive properties, and the properties are a function of temperature, pressure, and amount of the substance. That means number of moles. So X is a function of TPN. That is, the property is a function of temperature, pressure, and number of moles. Hence, X is said to be a dependent variable which depend upon the value of T, P, and N, which can be varied independent of each other and called independent variables. We can take the case where we keep two variables, suppose pressure and the number of moles constant, and vary the other variables. So if X is, and here X is a function of temperature, pressure, and N. And if we will take the derivative of X, that will dx. So in this case, if we want to take the derivative of X, then you should take the individual derivative, that is called a partial derivative. So dx equals to del x by del t dt at constant pressure and constant number of moles, plus del x by del p dp at constant temperature and constant number of moles, plus del x by del n at constant temperature and constant pressure. So where the differential in the first term, so here you can see, so in the differential, the first term, this term represent the change in properties of the X when temperature of the system is changed, while keeping the pressure P and amount or the number of moles N constant. In other words, this term represents the rate of change of property X as a function of temperature when P and N are constant, where dt represents the total change in temperature. The differential in the second term, the differential in the second term represent that is del X by del P at constant temperature and constant number of moles represent change in property of the X when the pressure is changed, maintaining temperature and number of moles constant. And similarly, the third term, that is del X by del N at constant temperature and pressure, represent the change of the property X, keeping number of change of the property X when the number of moles N changes, keeping temperature and pressure as constant. Now let us extend the argument for a binary solution which has Na number of moles of component A and Nb number of moles of component B, and work out the corresponding expression for changing property X. So if we extend this argument to a binary solution, if the binary solution will be formed by two components A and B, and the number of moles of A is Na and the number of moles of B will be Nb, then the thermodynamic property in this case will depend upon temperature, pressure, and number of moles of A, that is Na, and number of moles of B, that is Nb. Therefore, the expression for the X will be changes. So that is X equals to function of T, P, Na, and Nb. Now, if we take the differential form, then dx equals to del X by del T P and at del X by del T dt at constant pressure, constant number of moles of A, and constant number of moles of B. And similarly, plus del X by del P dP at constant pressure, constant number of moles of A, constant number of moles of B, plus del X by del Na dNA at constant temperature, pressure, and constant number of moles of B, plus del X by del Nb dNb at constant temperature, constant pressure, and constant number of moles of A. So you can note that the thermodynamic property X changes with change in the temperature, pressure, number of moles of A, and also number of moles of B. Now, if in this condition we will keep the temperature and pressure as constant, because if we perform this type of experiment in the laboratory, so at a particular environmental condition, the temperature and pressure will remain constant. So if the temperature and pressure will remain constant, then dt will be equals to 0 and dp will be equals to 0. And this equation 11, then the two terms of this equation 11 will be cancelled out, because at constant temperature and pressure dt will be 0, so this term will become 0. And similarly, this term dp will be 0, so this term will also become 0. And hence we will find out dx equals to del X by del Na dNA at constant temperature, pressure, and constant number of moles of B, plus del X by del Nb dNb at constant temperature, pressure, and constant number of moles of A. So here in this expression 12, the two terms del X by del Na T, P, Nb and del X by del Nb T, P, Na are called partial derivatives of the properties, with respect to number of moles of the component, that is Na and Nb. So these terms are known as partial molar properties. Here del X by del Na Tp and B represent the partial molar property for the component A, while del X by del Nb Tp and A represent the partial molar property of the component B. So here we will find out the partial molar component of the partial molar properties of the component A, that is this one. This one is the partial molar property of the component A, and this is the partial molar property of the component B. Now, to understand the physical significance of the term partial molar property, let us consider a situation where we will take a large volume of a binary mixture and one mole of component A to it. So initially we will take a large volume of a binary mixture, and that means we will take a large volume of binary mixture A and B, and to that mixture, if you will add just one mole of the component A, then the change in number of moles of A, that is DNA, will be equal to 1. because to a large volume of a binary mixture of A and B, we have added just 1 mole of component A. Since we have taken a large volume, then the mole fraction of the component B practically does not change upon addition of just 1 mole of component A. So the DNB will become 0, and in this situation dx equals to del x by del Na TPNB. Thus the partial molar property of a component A in a mixture can be defined as change in the property X. So here we are not mentioning a particular property. Here we are taking X as the extensive property. So the extensive property may be volume, may be internal energy, may be enthalpy, may be Helmholtz function, may be Gibbs function, whatever may be. In general term, here we are considering X as a partial molar property. So the partial molar property of the component A in a mixture can be defined as the change in the property X of the mixture when 1 mole of the component A is added to large volume of a mixture at constant temperature and pressure while keeping the amounts of the remaining components constant. Now the partial molar properties are represented as XIM, or simply you can write X bar I, where the subscript I represents the component whose amount is being varied, and the subscript M or a bar on the top of the symbol of the property indicate the property to be molar property. Using such representation for partial molar properties, you can write dx equals to xam dna plus xbm dnb. So here x just represent this one del x by del na. So here xam is del x by del na at constant temperature, constant pressure, and constant number of moles B. And similarly, xBm is del x by del NB at constant temperature, constant pressure, and constant number of moles of A, that is Na. Here, del x is the total change in the property X due to change in composition at constant temperature and pressure. Now coming to a general expression and the symbol and the corresponding symbol for the different partial molar properties of a binary mixture. So if the thermodynamic property, if the extensive thermodynamic property will be volume, then volume will be a function. So here we are considering for binary mixture, if we are taking the extensive thermodynamic property as volume, then V equals to function of temperature, pressure, Na and Nb, and the name of the partial molar property will become partial molar volume, and the symbol can be represented as VIM or VI bar, and VIM or VI bar stands for del V by del Ni TPNJ. Here I is the number of moles of the ith component, and J is the number of moles of jth component. And similarly, if you take internal energy, this is another partial molar property. U is a function of Tp, Na and Nb, that is called partial molar internal energy. So the representation will be UIM or UI bar, and the expression will be del U by del Ni TPNJ. And if we take another partial molar properties, enthalpy, H is a function of Tp, Na and Nb, that is called partial molar enthalpy. Similarly, the representation will be HIM or HI bar, and the expression will be del H by del Ni TPNJ. And if we take entropy, this is also another type of extensive property, that is also a function of temperature, pressure, and number of moles of A, number of moles of B, that is called partial molar entropy, that can be represented as SIM or SI bar. The expression will be del S by del Ni TPNJ. And if we consider another extensive property Gibbs energy, that is G, which is a function of temperature, pressure, number of moles of A and number of moles of B, then that is called partial molar Gibbs energy. and the other name of the partial molar Gibbs energy is chemical potential. So this is the other name of partial molar Gibbs energy, that is called chemical potential. The representation or the symbol of chemical potential is GIM or GI bar. It is also represented as mu I, that we will discuss later, and the expression will be del J by del Ni Tp Nj. If we extend the argument with multi-component mixture, so here up to this we have discussed about the single component, and if we extend this argument for multi-component mixture, uh, then the thermodynamic property will depend upon the temperature, pressure, Na, Nb, and the amount of the other components also. Then X equals to function of temperature, pressure, Na, Nb, Nc, Nd, etc. For infinitesimal change of temperature, pressure, and the number of moles of all other components, then the change of the properties of the X. So that means differential form will become dx equals to del x by del t at constant pressure and constant number of moles of all the components dt plus del x by del p at constant pressure, sorry, here that will be constant temperature. So the p will be here, the p will be t, del x by del p at constant temperature and constant number of moles of all the component dp plus del x by del Na at constant temperature, pressure, and constant number of moles of the second, third, fourth component, etc. Here there will be variation of the first component A. And similarly, the next term will be plus del x by del Nb, temperature, pressure at constant temperature, pressure, constant number of moles of the first component, constant number of moles of the third component, and so on. That means here there will be variation of number of moles of the second component, plus del x by del Ni Tp Na Nb Nj dni. So here at constant temperature, constant pressure, constant number of moles of the first, second, etc. component, only the ith component will be varied. Now, if you will extend this expression at constant temperature and pressure, then at constant temperature and pressure, then at constant temperature and pressure, dt will be equals to 0 and dp will be equals to 0. So the first two terms will be cancelled out at constant temperature and pressure. So we can write dx equals to del x by del Na Tp Nb Nc Nd dna plus del x by del Nb Tp Na Nc Nd dnb plus del x by plus del x by del Ni Tp Na Nb Nj dni and so on. So using the representation of partial molar quantities, the expression becomes dx equals to xam dna, xbm dnb, xim dni, and so on at constant temperature and pressure. So up to this, we have discussed about the partial molar quantity of any type of extensive thermodynamic properties. And after that, we will particularly discuss about different thermodynamic properties. So the mole fraction of the component A and the mixture containing Na moles of A and Nb moles of B, that can be written as, so if the mixture contains a binary solution, that is Na moles of A with Nb moles of B, then chi A equals to Na by Na plus Nb, so which is equals to uh, and here Dn equals to Kn minus N. So that is, so here Dn equals to Kn minus N, that is equals to N into K minus 1. So here chi A and chi B are not changing with change in the amount of A and B. And substituting the values of DNA and DNB in this equation, we can found dx equals to xam chi A dn plus xbm chi B dn. So this is equation number 24. So the equation number 24 need to be integrated to find. So we need to integrate the equation number 24. So this equation needs to be integrated from the initial amount n of the mixture to final amount kn. Since x is an extensive property and if n changes by k times, x will also changes by k times, and therefore the limit of the integration will be from x into kx in the left hand side and n into kn in the right hand side. So integrating the equation 24 with proper limit, we can write here, we can write kx minus x equals to x am chi a plus x bm chi b into whole into integration of dn from n to kn. And simplifying this expression, we can write x equals to summation of xim ni. So now we will discuss partial molar volume. So here we will take the partial molar volume. If volume of a binary solution, the volume of a binary solution which depends upon temperature, pressure, and amount of A and the amount of B, then the partial molar volume V is, so if we consider a binary solution forming by number of moles of A Na and number of moles of B Nb, then the volume is a function of T, P, Na and Nb. So this is equation 30. So using equation 12, we can write the expression. So it will change the differential form at constant temperature and pressure, then the first two terms will be 0 because at constant temperature dt will be equals to 0 and at constant pressure dp will be equals to 0. So deleting the first two terms, we can write dv equals to del v by del na tpnb dv equals to del v by del na dna at constant temperature and nb plus del v by del nb dnb at constant temperature, pressure and na. And here the first term of this expression 31, that is del v by del na tp number of moles of B is partial molar volume of A. And similarly, the second term, this one, is equals to partial molar volume of B. So now suppose if we add 1 mole of component of A to the mixture at constant temperature and pressure, then the number at constant number of moles of B. In such cases, DNA will be equals to 1 and DNB, because we are not adding B, we are only adding 1 mole of A. So the change in number of moles of A, that is DNA, equals to 1, and the change in number of moles of B, DNB, will be equal to 0. And substituting these values in equation 31, the second term will again become 0, and finally we will write dV equals to del V by del Na at constant temperature, pressure and number of moles of B. So this expression provides a definition of partial molar volume. Thus, the partial molar volume of component A in a binary mixture may be defined as the change in volume of a mixture when 1 mole of the component A is added to a large volume of mixture at constant temperature, pressure, while keeping the number of moles of the other component B as constant. Now, the unit of partial molar volume is liter per mole or decimeter cube per mole. Now, using the notation of partial molar properties as given above, we can write the expression for the change in volume in a binary mixture in terms of partial molar volume. of the component A and B. So in that case, we can write dV equals to VAM DNA plus VBM DNB. So the total volume of the binary mixture when Na moles of the component A are mixed with Nb moles of the component B can be obtained by integrating this expression, and that will become V equals to VMA Na plus VMB Nb. So now if we will discuss the physical insight or physical significance of the partial molar volume. So the concept of partial molar volume by taking the concept of partial molar volume by taking the example of binary solution containing water and methanol. Suppose water is the substance A and methanol is the substance B. Then the partial molar volume of the methanol here will rate at which the volume of the binary solution changes with the amount of methanol added to a large volume of the mixture at constant temperature and pressure. That means that is equals to VBM, which is equals to del V by del NB at constant temperature, pressure and constant number of moles of A. At 25 degrees Celsius and 1 bar, that means at room temperature and environmental condition, at room temperature and environmental pressure, then the molar volume of pure water, that is VMA star, which is equals to 18.07 ml per mole. So and that of the pure methanol, that is VMB star, equals to 40.75 ml per mole. When we mix 100 ml of water at 25 degrees Celsius with 100 ml of methanol at same temperature, it is found that the volume of the resulting mixture will not become 200. The volume of the resulting mixture will become 193.1 mole and not equals to 200. So let us first calculate the composition of the mixture, how it will become that. So the number of moles of the number of moles of A, that is Na, that means the number of moles of water equals to Va star divided by Vma star, which is equals to 100 ml divided by 18.07 ml per mole, which is equals to 5.53 mole. And similarly Nb equals to 2.45 mole. Then if you calculate the mole fraction of the B, that will equals to 0.307. Now if we prepare a mixture by mixing 5 ml of water and 5 ml of methanol, 50 times the volume used above in the case, the volume of the mixture will also 50 times, that is 9.655 ml. And it will have the same mole fraction of the methanol, that is 0.305. So here in the first case we have added 10 ml of methanol with 100 ml of methanol with 100 ml of water, and we will find the mole fraction of the methanol will be 0.307. And similarly if we add 5 ml of methanol and 5 ml of water to form a solution, then the mole fraction of methanol will also become same. So here on mixing 40.75 ml, that is 1 mole of pure methanol to the above solution. So to the above solution if we add 1 extra mole of methanol, that is 40.75 ml of pure methanol to the above solution, it is observed that the volume of the solution is increased by 38.8 ml. Similarly, on adding 1 mole of the pure methanol to the solution prepared by mixing 10 ml of water and 10 ml of methanol, also the volume increases. So here also the volume increases by 38.8 ml. So let us calculate the mole fraction of this solution, and that is compared in the table number 2. So the data for calculating the mole fraction. So in the serial number 1 we have added 100 ml of water with 100 ml of methanol. So the 100 ml of water equals to 5.53 mole and 100 ml of methanol, that is equals to 2.45 mole. Then the total observed volume will become 193.1. Then the mole fraction of water will be 0.693 and mole fraction of methanol will be 0.307. And if you add the mole fraction of both, that will the total mole fraction will become 1. And similarly, if we take 500 5 liter of water plus 5 liter of methanol, then the observed volume will become 9.655 liter, that is 9,655 ml. So here the volume is in ml. So here also the mole fraction of water will be same, that is 0.693, and mole fraction of methanol will also same, that is 0.307. And upon to this solution, so here in the second case we have taken 5 liter, that means 5000 ml of water, and added with 5000 ml of methanol, then the observed volume will become 9655, and the mole fraction of water will become same, that is 0.693, and mole fraction of water, that is XA or chi A, is 0.693, and mole fraction of methanol, that is chi B, is 0.307. That means if we take 100 ml of water plus 100 ml of methanol, the mole fraction of water and methanol will be similar to the solution where we will take 5 liter of methanol and plus 5 liter of water, the mole fraction will remain same. Now to this solution, so this is a large volume solution. To this solution, if we add 1 mole of extra pure methanol, so 1 mole of methanol is 40.75 ml. So if we add 1 mole of methanol, then the volume of water will not change, that is 5000 ml, which is 277.78 moles, and the volume of methanol will changes from 5000 to 5040.75 ml, that is 123.5 moles. And here in this case the observed volume will become 9693 plus 0.8, and here the mole fraction of water will be decreased from 0.693 to 0.6922, and the mole fraction of methanol will increase from 0.307 to 0.3078. And similarly, if in the third case, if you take 10 liter of methanol plus 10 liter of 10 liter of water plus 10 liter of methanol, then the observed volume will become 19.31 liter, and the mole fraction will remain same in the first case. So this is a very large volume of the solution, and upon to this solution, if you add one extra mole of pure methanol, then the volume of water will remain same, but the volume of methanol will change from 10,000 ml to 10,040.75 ml, and here you will observe that there will be no change in mole fraction of the water and also mole fraction of the methanol. That means very negligible change, and the number of moles of water and methanol will remain same. So the amount of methanol in the example above is not infinitesimal, but it is quite small as compared to the amount of the initial mixture. Therefore, as shown in the table number 1, there is a very little change in composition of the mixture. We can say that in this addition, the mole fraction of the water remains practically constant, and the observed change in volume of the mixture by adding 1 mole of methanol is the partial molar volume of methanol, and it corresponds to change in volume per mole of the methanol at constant temperature, pressure, and constant number of moles of A. In other words, in this case, we can write VMB, that means partial molar volume of methanol, equals to del V by del NB at constant temperature, constant pressure, and constant number of moles of water, that is equals to del V by del NB, which is equals to 30.8 ml per mole. So here one question is there: the partial molar volume of water and methanol in a solution having 5.53 mole of water and 2.45 mole of methanol at 25 degrees Celsius or room temperature, 298 Kelvin and 1 bar pressure are this and this. Calculate the total volume of the solution. So the total volume of the solution V equals to VMW plus NW, W stands for water, plus VMM plus NM. Here the capital M stands for methanol, and here given that number of moles of water equals to 5.53 mole, number of moles of methanol equals to 2.45 moles, and VMW equals to 17.73 ml per volume per mole, and VMM, that is Vm methanol, equals to 38.8 ml per mole. By substituting these values, the total volume of the solution will become 193.16 ml. So the total volume will not become 100 ml, 200 ml, that will become 193.16 ml. Now the second question, calculate the volume of the pure methanol and pure water at 25 degrees Celsius that must be mixed to form 1000 ml of solution of methanol in water having a mole fraction of 0.3. Means the mole fraction of methanol is 0.3. The molar volumes of pure methanol and water and their partial molar volumes of the composition are given here. So here we know that V equals to this, and putting the values we can find out V equals to 24.03 ml per mole. So hence the total number of moles will become, since we needed 1000 ml of the mixture, then the total number of moles will be 41.61 mole, and hence the number of moles of methanol equals to mole fraction of methanol into total number of moles, that is equals to 12.48 mole. And similarly the number of moles of water equals to mole fraction of water. So as the mole fraction of methanol is given as 0.3, then the mole fraction of water will become 0.7 into total number of moles 41.61, then that will become 29.13. And finally the volume of each pure species required, that is given, so here finally Vm equals to 12.48 into 40.73, that is equal to this, and similarly Vw will find out. And after calculating the individual volume, we can write the total volume of the solution. We can add the total volume of the solution. Now coming to volume of mixing. Volume of mixing. So del mix V, that is volume of mixing, equals to VAM Na plus VBM NB. So if we mix the total, mix 100 ml of A and 100 ml of B, the total volume will not become 200 ml. So the total volume will become 200 ml minus something. So here V mix, del mix V equals to VAM Na plus VBM NB minus VAM star Na plus VBM star NB. Here the sum of the first two terms gives the volume of the solution. So this is, so the first two terms give the volume of the solution, and VAM star and VBM star are the molar volumes of the pure A and pure B components respectively, and the term in the bracket, this one, is the sum of the volumes of the pure A and B component. So the volume of mixing of the two components can be zero or non-zero depending upon the nature and magnitude of the intermolecular forces, intermolecular interaction between them. So that can be zero or that can be non-zero. When the interaction between the molecules of the two component AB is equals to the interaction of AA and interaction of BB, then the volume of mixture equals to total volume of the pure component. That means in this case the bracket, the term in the bracket will become zero, and hence the del mix B will be become zero. Such solution is a mixture is known as ideal solution or ideal mixture. Now, so in that case, the V equals to VAM star Na plus VBM star NB. So this is equation number 40. So the equation dividing equation 40 throughout by total amount or the total number of moles of the solution, we get the expression mean molar volume. So the mean molar volume Vm equals to total V by N means total number of moles. So that is equals to VAM star Na by N plus VBM star and V by N. And here we can also write Vm equals to, so here Na by N is nothing but mole fraction of A, that is chi A, and Nb by N is nothing but mole fraction of B, that is chi B, and hence we can write mean molar volume Vm equals to Vam star chi A plus Vbm star chi B. Now if we plot a graph between the molar volume of the solution versus the mole fraction of the component B. So in the x-axis we will find the mole fraction of the component A, that is chi A, and in the y-axis we will write molar volume Vm. So here this is molar volume Vm. So if we draw a graph, we will find a straight line with intercept as Vmax. So here the intercept will be Vam star, and at xb, so at x, when chi b equals to 0, that means mole fraction of b will be 0, that means pure component of A, right? So at this situation only pure component of A will be there, because the mole fraction of B will be equals to 0. So here in the right side y axis, the intercept will be Vam star, and similarly when the mole fraction of A will be 0, only that is for the pure component of B only, the mole fraction, the intercept will become Vbm star. So this is for ideal solution. But when the interaction between the unlike molecule of the two component AB, that means if the interaction between AB is not equal to the interaction between the molecules pure AA and pure BB, then the volume of the solution is not equal to sum of the volume of the pure component. So in this case, that is called a non-ideal solution. So for non-ideal solution, del mix V is not equal to 0. That means that it have some value. So in that case, VAM plus VBM is not equals to VAM star. Star means for pure component. VM star Na plus VBM star NB. So here two cases will be arise. The two cases will be if the interaction between the component A and B is greater than the interaction between pure A and the interaction between pure B and B. So that means individually when A was there, the interaction between the molecules and for individually B, the interaction will be B and B. But when we mix, if the interaction between A and B will be more, so in that case the volume decreases, because due to more interaction or strong interaction. So that is one case, and the second case will be if the interaction between A and B is less than the interaction between pure AA and interaction between pure BB. So in that case, when we mix A and B, then the volume increases as the interaction between A and B decreases. So in case of non-ideal solution, the volume of the solution varies non-linearly with concentration. In the first case, we have discussed that for ideal solution, then the volume of the solution varies linearly with respect to mole fraction. But here, for non-ideal solution, then the volume of the solution varies non-linearly with concentration or mole fraction. Then the nature of variation of the volume of the solution will depend upon the nature of the magnitude of AA, BB, and AB intermolecular interaction between the two components. These interactions will be different in volume of mixing, and accordingly the nature of the variation. So in the first case, at the then the nature of the variation of volume for the non-ideal solution with concentration will be any one of the four possible types. So these types along their representation plots are there. So these are the four possible type of representation. So in the first type, if the interaction between A and B is always less than the interaction between AA and BB, then the volume will increases. And here the dotted line represent the ideal volume, but this is the solution of ideal, non-ideal solution. And in the second case represents the if the interaction between A and B is more than the interaction between pure AA and pure BB, then in that case the volume decreases than that of the ideal volume. And in the third case, initially the del mix V is greater than 0. That means initially the interaction was less, but upon addition of more amount of A to the solution, the interaction will become stronger interaction, and in that case the volume decreases. So this is the third case. And in the fourth case, initially there will be strong interaction between A and B. Upon addition of small amount of A to B, the interaction will be stronger. But upon addition of more amount of A, the interaction will become weaker and the volume increases. So that is in the fourth case. Now coming to experimental determination of partial molar volume. As explained above, the mean molar volume. So here I will take just 2-3 minutes of break, and after that again we will continue. Hello. So now we'll continue. So here we will continue experimental determination of partial molar volume. So as we explained above, the mean molar volume for non-ideal binary solution is given as Vm equals to Vam chi A plus Vm chi B, and since we know that the total mole fraction chi A plus chi B equals to 0, now in this case, in place of chi B, we can substitute 1 minus chi A, and hence the equation 44 will become Vm equals to Vam chi A plus Vbm 1 minus chi A. That means in place of chi B, we have just written 1 minus chi A. Now rearranging this equation 45, we can write Vm equal to Vam minus Vbm whole into chi A plus Vbm. Thus, according to equation 46, a plot of mean molar volume as a function of the mole fraction of the component A will be a straight line with slope and intercept. So here, if you plot a graph based upon the equation 46, so here the by taking mole fraction of A chi A on the x-axis and Vm in the y-axis, so the nature of the graph will be a straight line with slope. So this will be the slope. That means y, just like y equals to mx plus c, mx plus c, y equals to mx plus c. So here in the x you will take x-axis, y in the y-axis, m is nothing but the slope of the graph, and c is the intercept of the graph. So if you compare this equation to y equals to mx plus c, then we will find out that the nature of the graph will be a straight line with slope Vam minus Vbm and with intercept Vbm respectively. In a typical experimental determination of partial molar volume, a series of binary solution A and B are prepared with varying the mole fraction of A. Thus, the volume of each solution is measured and the mean molar volume is calculated for each component. A graph of Vm is then plotted against the mole fraction of the component A. This graph may or may not be a straight line depending upon the nature of the two components as discussed above. A linear plot suggests that the partial molar volume are independent of the composition and are expected to be equal molar volumes of the respective pure component, that is in the case of ideal solution. But in case of non-linear variation of the mean molar volume with mole fraction of the component A, then the molar volume of the component VAM and VBM are dependent upon the composition of the solution. That is, at each value chi A, the partial molar volume are different. However, for a given composition, Vm and Vbm are constant. Therefore, the slope of the tangent drawn at any given point, the curve along the corresponding intercept can be used to calculate the partial molar volume of the two components for the composition corresponding to that point. So the slope of the tangent will become del Vm by del xa or del chi a, which is equals to this. So this is the slope of the graph. Further, from equation 46, the intercept of the tangent chi a star, chi a dash is equals to Vmb. Therefore, that to determine the partial molar volume at a given composition, chi a dash and chi a dash will be a tangent to the curve drawn at chi a
Hello,
dash, and the slope intercept are measured. So by measuring the slope and intercept, we
hello,
can find out
sir.
hello, hello,
Hello.
hello.
हाँ सर नमस्कार. Hello,
Hello, am I audible?
sir. Yes, sir. Sir,
Okay, tell me.
uh, ଏଇ ଏଇ ଯୋଉ ଚାପ୍ଟର ଯାକ ପଢା ହଉଛି ସାର୍ ସେଇଟା କ୍ୱେଶ୍ଚନ ଆନ୍ସର ଫର୍ମାଟରେ ପଢେଇଲେ ଟିକେ ବେଟର ହବ କି?
Question answer.
ଫର୍ମାଟରେ ବୋଲେ
Hello.
କୌଣସି ଗୋଟେ କ୍ୱେଶ୍ଚନ ନେଇକି ତା ସାର୍ କୌଣସି ଗୋଟେ କ୍ୱେଶ୍ଚନ ନେଇକି ତା ଆନ୍ସର ଯାକ ଏମିତି ଏମିତି ଲେଖା ହବ ଏତିକି ଲେଖା ହବ ସେଇଟା ଟିକେ ବତେଇଦେଲେ ଭଲ ହବ ସାର୍।
ହଁ ଦେଖ, ଫାଷ୍ଟ ଆମେ କଣ୍ଟେଣ୍ଟ ଟା କମ୍ପ୍ଲିଟ କରିବାକୁ ପଡିବ ଯୋଉଟା ଅଛି। ତାପରେ ତମର ଏଠି ସବୁ କ୍ୱେଶ୍ଚିନ୍ ଦିଆଯାଇଛି। ଆଫ୍ଟର ଦ୍ୟାଟ ତମ ଦେଖିପାରିବ ସବୁ ଡିଫରେଣ୍ଟ କ୍ୱେଶ୍ଚିନ୍ ଅଛି। ଫାଷ୍ଟ କିଛି କ୍ୱେଶ୍ଚିନ୍ ଦିଆଯାଇଛି, ତାର ସଲ୍ୟୁସନ ବି ଦିଆଯାଇଛି। ସପୋଜ ମୁଁ କହୁଛି ଗୋଟେ କ୍ୱେଶ୍ଚିନ୍ ଆସିବ। ବର୍ତ୍ତମାନ ଯୋଉଟା ଆମେ ପଢୁଛୁ କ୍ୱେଶ୍ଚିନ୍ ଆସିବ କଣ ନା ହାଉ ଟୁ ଡିଟରମିନ୍ ପାର୍ସିଆଲ ମୋଲାର ଭଲ୍ୟୁମ ଏକ୍ସପେରିମେଣ୍ଟାଲି ହେଲା। ତ ଡିଟରମିନେସନ ଅଫ ପାର୍ସିଆଲ ମୋଲାର ଭଲ୍ୟୁମ ଏକ୍ସପେରିମେଣ୍ଟାଲି, ଏଇଠି ଯାହା ଅଣ୍ଡରଲାଇନ ହେଇଛି ସେତିକି ହିଁ ତମକୁ ଲେଖିବାକୁ ପଡିବ। ତ ହିୟର ମାନେ ମୁଁ ଏ ନୋଟରେ ଅଲରେଡି ଅଣ୍ଡରଲାଇନ କରିଦେଇଛି, ରାଇଟ। ତ ତମକୁ ଯଦି କ୍ୱେଶ୍ଚିନ୍ ଆସିବ କାଲକୁଲେଟ, ଏଇଟା ଗୋଟେ ଲଙ୍ଗ କ୍ୱେଶ୍ଚିନ୍ ଆସିପାରିବ। डिटर्मिनेशन ऑफ पार्शियल मोलार वॉल्यूम, एक्सपेरिमेंटल डिटर्मिनेशन ऑफ पार्शियल मोलार वॉल्यूम, जहां तमर अंडरलाइन हेची से आसीबो। सो दिस इज अ वेरी सिंपल थिंग माने से कोन कहूची ना, एठी हम गोटे ग्राफ नबा, को ग्राफ नबा बेस्ड अपॉन दिस इक्वेशन। एई जो इक्वेशन को बेस करके हमें ग्राफ ड्रॉ करिबा। तो जोठी एठी सो आकु जदि हमें कंपैरिजन करिबा y equals to mx plus c को, we know that the nature of the graph of y equals to mx plus c is nothing but a straight line. तो m हला तार स्लोप, तो y equals to mx plus c रे वेरिएशन होची कि y वेरिएशन होची x वेरिएशन हो। तो एठी v vm y जगह रे vm अछि, x जगह रे एठी हमें देखि पारुथबा इक्वेशन 4.6 रे y जगह रे vm अछि, x जगह रे काय अछि, आउ c जगह रे अछि कोन vbm अछि, आउ एटा हला स्लोप। दिस वन इज द स्लोप। सो y इक्वल टू mx प्लस c रे गोटे ग्राफ प्लॉट कला परे आमे तार जो स्लोप आसीबो, स्लोप रु पाई दिबा vam माइनस vbm, आउ तार इंटरसेप्ट आसीबो सेथिरु आमे पाई दिबा vbm। तो सेठू इंडिविजुअली vbm आउ vam ता बाहर पड़ी। if the nature of the graph will be straight line, तापर कहूची the nature of the graph will be straight line only for ideal solution, but if the solution will be non-ideal solution, then the nature of the graph will not be a straight line, that may be a curve. So if the nature of the graph will be a curve, that is for non-linear variation, that is for non-ideal solution, then we can find out the value of VAM and VBM by drawing a tangent to the curve. तो कर्व को गोटे टैंजेंट ड्रॉ करके हमें पाई परिबा। तो सेही जिंसटा एठी सेटा एक्सप्लेन करा जाय। सो दिस इज वन लॉन्ग क्वेश्चन। ओके, so in the first part we have discussed that partial molar volume. First हमें discussion कले partial molar volume, and after that we will discuss chemical potential, because we know that chemical potential is nothing but that is the partial molar gives energy. Partial molar gives energy. So the partial molar gives energy ताकू rename करा जायछि as chemical potential. The partial molar gives energy are also important to study the chemical equilibrium and phase equilibrium. Due to the importance of partial molar gives energy in thermodynamic studies, it was given a special name, that is chemical potential. So the chemical potential is represented as mu and is defined as, already हमें first रे तार definition दी to mu I equals to del G by del Ni T P Nj. Nj means here the number of moles except ith component. All the number of moles of all the component will maintain constant. Only the number of moles of the ith component will be varying. So this is the chemical potential of the ith component of a solution, that is mu I equals to del G by del Ni Tp Nj. That is, the chemical potential of the ith component mu J refers to, sorry, the chemical potential of the ith component mu I refers to the rate of change of Gibbs energy with change in number of moles of the ith component when temperature, pressure and number of moles of the other component will kept constant. Again, I am repeating here, the chemical potential of ith component in a mixture refers to the rate of change of Gibbs energy with change in number of moles of ith component when temperature, pressure and number of moles of all other components are kept constant. Because we know that Gibbs energy is an extensive property, so so if we discuss in a binary solution, the Gibbs energy is an extensive property, and that is a function of, that is G is a function of T, P, Na and Nb for binary solution. Now, if we take the differential of this form, dG equals to del G by del T dt at constant pressure Na and Nb. So that means in the first term, the first term deals with the change in Gibbs energy with respect to change in temperature only. The second term deals with the change in Gibbs energy with change in pressure only. The third term deals with the change in Gibbs energy with respect to change in number of moles of A only. The fourth term deals with the change in Gibbs energy with respect to change in number of moles of B only. That means in the first term, only the temperature changes, the number of moles of A, number of moles of B, and pressure remaining constant. In the second term, only the pressure changes, the temperature, number of moles of A, number of moles of B will remain constant. In the third term, only number of moles of A changes, but the temperature, pressure, and number of moles of B remain constant. In the fourth term, the number of moles of B changes, and the temperature, pressure, number of moles of A remain constant. But, and in the previous unit, in the yesterday class, we have studied that from the Maxwell's relationship, del G by del T at constant pressure, constant number of moles of A and constant number of moles of B is nothing but that is equal to minus S. And similarly, del G by del P at constant temperature, constant number of moles of A and constant number of moles of B equals to volume. Now, putting these two Maxwell's relationship, these two equations of Maxwell's relationship in equation number 50, we can write at constant temperature and pressure, we can write, sorry, and again, the third term, this one, that is del G by del Na, that is change in Gibbs free energy with respect to change in number of moles of A only at constant temperature, at constant pressure, and constant. So here you will write P. There is a printing mistake. You will write P here. P at constant temperature, constant pressure, and constant number of moles. That is nothing but the chemical potential of A. And similarly, the fourth one. So these two are from Maxwell's relationship, and this is the third term is nothing but the chemical potential mu A, and similarly the fourth term is nothing but the chemical potential of B, that is mu B. So putting all the four terms in equation 50, we can write dg equals to minus sdt plus vdp plus mu A dna plus mu B dnb. Now, so this is equation 53. Now at constant temperature and constant pressure, the first two term will become 0 because dt will be equal to 0 and dp will be equal to 0. Therefore, the equation can be written as dg equals to mu A dna plus mu B dnb. So this expression gives the change in Gibbs energy with change in composition of a binary mixture at constant temperature and pressure, and using equation 25 and replacing x by g, then the total Gibbs energy of a binary mixture can be written as g equals to, that means if you take integration of this equation 54, then integration of the LHS of this equation 54 will become g, and similarly integration of the RHS will become mu a Na plus mu b Nb. So that means g equals to mu a Na plus mu b Nb. This gives the total Gibbs energy of a binary mixture at a fixed temperature and fixed composition. Now for a pure component, if you take only pure component A, so in that case B will not be there, so G equals to mu a Na. And rearranging, we can write mu a equals to G by Na. So this expression implies that the chemical potential of a pure substance is equal to molar Gibbs energy of a substance. That means Gibbs energy of a substance, total Gibbs energy G divided by number of moles. So that is called molar Gibbs energy of a substance. So the chemical potential of a pure substance is nothing but that is the molar Gibbs energy of a substance. So now coming to the significance of chemical potential. So the chemical potential can seen as escaping tendency of a substance in a mixture. The molecules of a component spontaneously move from the region of high chemical potential to the region of low chemical potential in a mixture. This continues till the chemical potential of the component becomes same throughout the system. For example, if we add a drop of ink in some water taken in a beaker, then the molecule of the ink in the region of drop gradually but spontaneously spread out. So it will spread up till the chemical potential of the ink will remain same throughout the solution. So this is a concentration gradient, and the molecule at higher chemical potential moves spontaneously to the region of lower chemical potential. So that gives, so this is the figure. So this is the drop of ink and these are water. So gradually that will spread throughout the container. The figure gives a schematic representation of concentration gradient. So you can see this is the drop where the concentration will be more, and in the water the concentration will be less, and if when the concentration will be remain same, then the chemical potential will be same. So this figure gives the schematic representation of a concentration gradient. The species inside the porous membrane diffuse out the region of lower chemical potential outside the membrane. The process continues till the concentration becomes equal to throughout the system. So this is about chemical potential, and after that we will discuss the effect of temperature and pressure on chemical potential. First we will discuss the effect of temperature on chemical potential, and after that we will discuss the effect of pressure on chemical potential. So the first one is effect of temperature on chemical potential. To study the effect of temperature change on chemical potential for a system, we need to differentiate the expression of chemical potential with respect to temperature, right? Because we know that so the chemical potential is mathematically defined as the chemical potential of any component I is mathematically defined as mu I equals to del G by del Ni at constant temperature, constant pressure, and constant number of moles of all the component except ith component, that is Nj. Now differentiating this equation with respect to temperature while keeping the pressure and composition constant, we can write differentiating the LHS, differentiating the expression with respect to temperature, because here we are studying the effect of variation of temperature on chemical potential, and hence we will differentiate the chemical potential with respect to temperature. Then the LHS will become del mu I by del T at constant P constant number of moles of ith component and number of moles of jth component. That means the number of moles of all the component at uh, at constant number of moles of all component at constant pressure, which is equals to, if you take the derivative with respect to T of on the RHS, that will become del by del T, this term, this one. According to the Euler's theorem, so from the Euler's theorem, we can write del by del T, del G by del Ni equals to del, that means only exchange will be there. According to the Euler's theorem, here the del T and del Ni will exchange with one another. So after exchanging, we know that del G by del Ni is nothing but minus S. So therefore, this term del mu I by del T at P at constant pressure and constant number of moles of all the component equals to, that means this one equals to del by del T, del G by del Ni, del by del T, this component, and this component is nothing but, and after that we'll applying Euler's theorem, we'll exchange this del T and del Ni. So that will become del by del Ni, del G by del Ni, P Ni Nj with at T P Nj. So that will become minus del S by del Ni T P Nj. And from the definition of partial molar property, we can write del S by del Ni Tp Nj equals to partial molar entropy. So this term will become minus S minus partial molar entropy. As you know that the absolute entropy is always positive, therefore the partial molar entropy has a positive value. So that indicating that this term is always negative, and it is clear from this relation that the chemical potential will decrease with the decrease in temperature. So d mu I equals to minus, so putting the different terms, we can write d mu I equals to minus SIM dt. Now on integrating the equation 63 with proper limits, integration of d mu I from mu I at temperature T1 to mu I at temperature T2 equals to integration of minus SIM dt from temperature T1 to T2, and simplifying this integration, the LHS will become mu I T2P minus mu I T1P, which is equals to integration of minus SIM dt from T1 to T2. So the extent of change in chemical potential with temperature will depend upon the partial molar entropy of the component. Now for a pure substance, the extent of change in chemical potential with temperature will depend upon the molar entropy of the substance. You know that the molar entropy of the substance in the vapor phase is maximum and in the solid phase is the minimum. So that means the molar entropy in the vapor phase, SVM, we know that the entropy, molar entropy of any substance in the vapor phase will be maximum entropy, and the molar entropy of any substance in the solid phase will be minimum, that is SVM is greater than SLM. So this is the molar entropy in the liquid phase, which is also greater than the molar entropy in the solid phase. So thus with increase in temperature, the entropy of the substance will decrease the most if the substance is in gaseous state. This expression is particularly useful in explaining the colligative properties like depression in freezing point and elevation in boiling point. And after that, we will discuss the effect of pressure change on chemical potential. So we will discuss the effect of pressure change on chemical potential from equation number 48. Now applying Euler's theorem to this, we can write this expression equals to VIM. Therefore, the expression becomes del mu I by del P at constant temperature and constant number of moles of any component, because here pressure will vary, is nothing but VIM. But if temperature will vary, remaining pressure and number of moles of all component constant, that will become minus SIM. entropy. But when pressure will change, maintaining temperature and number of moles of all the components, the term will become partial molar volume, VIM. The above equation can be written as d mu I equals to VIM dP. It implies that the chemical potential increases with increase in pressure. The extent of increase in chemical potential of a given for a given increase in pressure will depend upon the value of partial molar volume. Now coming to mixture of gases, as you above studied above that the chemical potential of a pure substance is same as the molar Gibbs energy. Further, you will recall in the previous unit the Gibbs energy, because in the previous unit in the last class, yesterday's class, we know that dg equals to minus sdt plus vdp. Now comparing the above equation to d mu I equals to minus sim dt plus bim dp. If you compare both the equations for a pure substance at constant temperature, the above equation, when temperature will constant, dt will be 0. So the above equation will become d mu equals to vm dp. This expression can be integrated to get the chemical potential value at different pressures at a constant temperature. So you will take the integral of this. However, since the molar volume is pressure dependent and the integration of the right side is not straightforward, in this case, solid and liquid, because we know that the molar volume is completely dependent upon the pressure, so this equation is not very much useful. But in case of solid and liquid, they are not easily compressed, so in that case the change in pressure, in that case the pressure will not change. So for small pressure range, the molar volume of a pure solid and pure liquid substance can be assumed to be constant. In such cases, the molar volume term can be taken out of the integral. Therefore, for pure solid and pure liquid, Vm will volume will molar volume will remain constant, so that will be taken out from the integral. But for gaseous substance, there will be change in molar volume with respect to change in pressure, so that will be inside the integral. But for solid and liquid, with change in pressure, there will be a negligible change in molar volume for solid and liquid substance. So the Vm will be almost constant, that will be taken out from the integral. Now, if P1 taken as the standard pressure and the chemical potential at 1 bar is the standard chemical potential of the substance, that is mu naught, therefore mu Tp equals to mu naught T, which is equals to Vm whole into P minus 1. Then the chemical potential of an ideal gas in terms of pressure. Now let us take the cases of gases, ideal gas. In this case, the molar volume changes with change in pressure. So for gases, we have to write the molar volume in terms of pressure. That means Vm, if you consider the ideal gas equation, Pv equals to nRT. For one more of gas, that is Pv equals to RT. So Vm equals to RT by P. Now putting the value of Vm as RT by P in the above equation, the integral will become like this, and integrating between the proper limits, so the value will become mu Tp2 minus mu Tp1 at constant temperature. So that's why T will remain constant, but there will be change in pressure P1 to P2, so the integral will be like this, and RT constant, so that will, so the two terms are taken out from the integral. We will find integration of 1 by P dP, so that is dln P. For initial pressure P1 equals to P naught, that is equals to 1 bar, and the chemical potential is equals to the standard chemical potential of the gas, and the equation will become mu Tp minus mu naught T equals to RT ln P by P naught. Since P naught is the standard pressure, that is 1 bar, then we can write mu Tp minus mu naught T equal to RT ln P, because standard pressure is 1. You can see from the above expression, the chemical potential of an ideal gas increases with increase in pressure. If the standard chemical potential of an ideal gas is known at a given temperature, then the chemical potential can be calculated at any other pressure and given temperature. Reminder that the standard conditions do not include the temperature, hence the standard chemical potential at different temperature will be different. Whenever the temperature is mentioned in the standard value, that is taken as, so if the temperature will be mentioned in the standard value, that will be taken as 298 Kelvin or 25 degrees Celsius. Now, chemical potential of a real gas. So, in the above expression, we have discussed that the chemical potential of ideal gas. But if we'll find out, if we want to discuss the chemical potential of real gas, that is termed as fugacity. The chemical potential of a real gas is termed as fugacity. In case of ideal gas, that is known as chemical potential, but in case of real gas, that is called fugacity. In case of real gas, the pressure is replaced in terms of fugacity F, and all the deviation arising due to intermolecular interaction are included in it. Therefore, the fugacity is known as corrected pressure, and it has the unit of the pressure. So, F is nothing but the fugacity equals to some constant gamma into P. Gamma is known as fugacity coefficient, which is having the value of 1 for ideal gas. So, for ideal gas, pressure equals to fugacity, but for non-ideal gas, gamma is not equals to 1. So, in that case, fugacity and pressure are different. At very low pressure, the fugacity coefficient can be approximately taken as 1, and that the gas behave ideally. So if you take the limit pressure tends to 0, gamma, when limit pressure tends to 0, gamma tends to 1, then for real gases, the equation will become mu Tp minus mu naught T RTLN F by P naught, which is equals to RTLN gamma P by P naught. So if P naught equals to 1 bar, then the equation can be written mu Tp minus mu naught T, which is equals to RTLN P minus RTLN gamma. Now the next one is chemical potential of an ideal gas is a mixture of ideal gases. So here we will take, so after 2-3 minutes again we will discuss. Now we'll discuss the chemical potential of an ideal gas in a mixture of ideal gases. The chemical potential of a particular ideal gas in a mixture of ideal gases. Whenever two or more gases are present in the system, that is known as a mixture of gases. During the study of thermodynamic properties of the gaseous mixture, it is easier to assume that the component of the mixture are ideal gases. But the thermodynamic expansions obtained for a mixture of ideal gases can be further modified to get the expression of mixture of gases. So here, for mixture of gases, the contribution of each gas, uh, uh, to the total pressure P is known as partial pressure, because if you take the mixture of different gases, and if P is the total pressure of the gas, then the contribution of individual uh, then the contribution of the pressure of individual gas is known as partial pressure of that component Pi. Suppose suppose in the mixture the total pressure is P, and to the total pressure P, if the contribution of pressure of the ith component of the gas is Pi, then Pi is called partial pressure of the ith component, and it depends upon the mole fraction of the component xi or chi. So that means if the mole fraction of the ith component will be more, then its partial pressure will be more. Then according to Dalton's law of partial pressure, we know that Pi equals to xi into total P. Now let us find how does the chemical potential changes when the pure ideal gas is added to a mixture of ideal gases. The change in chemical potential for a component at constant temperature is given by the expression d mu I equals to Vim dP. Already that this expression we have derived. So for ideal gas, since the partial molar volume is equals to molar volume, that means Vim equals to RT by P. Then the expression for the d mu I can be written as d mu I equals to RT by P dP, and that is nothing but RT dln P. To find the total change in chemical potential due to mixing, we have to integrate the above equation 85. If we integrate the above equation 85, we will find out the total change in chemical potential due to mixing of the different gases. Now let us take the initial state as pure gas having pressure 1 bar, and that is in the standard pressure P naught at any temperature T. Then integrating the above equation, we will use the proper limit. So in the left hand side, the limit will be mu I naught at temperature T to mu I at temperature T. Integration of d mu from mu I naught T at temperature T to mu I naught temperature, from mu I naught at temperature T to mu I at temperature T, which is equals to RT will be constant. So the two terms will be taken out of the integration, and integration of dln dp, dln dp, sorry, dln p. So that will become dln p, dln p dp, dln p dp from p naught to pi. And integrating this, we can find that the value will become mu I at temperature T minus mu I naught at temperature T. So this will be minus, not equal to, this will be minus. Some printing mistakes are there. You can carefully observe. So this will be minus, which is equals to RT ln Pi by Pi naught. Now coming to a very important equation. So definitely that may be one long question, that is called Gibbs-Duhem equation. As shown earlier, the change in extensive property X at constant temperature and constant pressure already we have discussed today. From the initially we have already discussed the value of the extensive property T at constant temperature and constant pressure. The change in the value of the extensive property T at constant temperature and constant pressure will become dx equals to xam dna plus xbm dnb. Here the term for temperature and pressure are deleted, because here we are considering the condition at constant temperature and pressure. So at constant temperature dt will be equals to 0, and at constant pressure dp will be equals to 0. So both the terms will be deleted, and hence we will find out at constant temperature and pressure dx equals to xma dna plus xnb dnb. Whereas the total extensive property at a given temperature and pressure and at a given composition can be find out by integrating this equation. So integrating this equation, we can write x equals to xma na plus xnb nb, and the differential form of equation 28 will be give the total change in x. So again, if we take the differential form, we can write dx equals to xma dna plus na dxa NaDXMA plus XMB plus NbDXMB. So this is equation 88. So that means again we are first we have taken this equation, and after that first we have taken this equation, and then we have taken the integration of this equation to find out this one, and after that again we have taken the derivative differential of this equation to find this one. And again, since both equation 24, this one and 88, since both the equation 24 and 88 represent the total change in state variable x, so both are equal. You can observe the LHS of both the equations are equal. So as the LHS of both the equations are equal, you can write, so that is XMA DNA plus XMB DNB equals to XMA DNA plus X DNA plus NA DXMA plus XMB DNB plus NB DXMB. And hence, comparing both, we can find out Na dxma plus Nb dxnb is nothing but equals to 0. That means both the summation of both the two terms will be definitely 0. So, and hence this equation 90 in the general form is a very important relation that is known as Gibbs-Duhem equation. This equation 90 is called Gibbs-Duhem equation. The Gibbs-Duhem equation can be written in terms of the volume also. So Na dVma plus Nb dVmb equals to 0. Or we can write Na dVma is nothing but equals to minus Nb dVmb. So this is the true for all type of partial molar quantities. Then the Gibbs-Duhem equation in terms of chemical potential can also be written as Na d mu A plus Nb d mu B equals to 0. If the changes in temperature and pressure are also considered, so initially we have taken the condition of constant temperature and pressure. So if changes of temperature and pressure are also considered, then the Gibbs-Duhem equation will become minus SdT plus VdP Na d mu A plus Nb d mu B equals to 0. So this is the Gibbs-Duhem equation for in terms of chemical potential if the temperature and pressure will change. But if the temperature pressure will remain constant, then the Gibbs-Duhem equation in terms of chemical potential will like this. So here few questions are there. For binary solution where Na equals to 3 Nb, if the chemical potential of A changes by 2 joule per mole, then what is the change in chemical potential of B? So this equation can be easily solved by using the above this one. In a binary solution of ideal gases in which Na equals to 5 Nb and the partial molar volume of B decreased by 0.01 meter cube per mole, what will be the change in partial molar volume of A? So this can be solved by using this above this equation. So here the temperature and pressure are not mentioned. That means you have to take at constant temperature and pressure. So this is about unit 2, and some terminal questions are there. From the terminal defined partial molar property, you can easily solve that one. So all these, so this is another numerical problem. Today we have also solved this type of numerical questions. And the third one is defined chemical potential. How will the chemical potential of an ideal gas change if the pressure of the gas increased at constant temperature? Complete derivation is there in your note. So that for an ideal gas mixture, the partial molar volume equals to RT by P. So this also completely there in your book. So that in a binary unit 2, and tomorrow we'll discuss the next unit, that is introduction to statistical thermodynamics. Tomorrow we will discuss about the statistical thermodynamics. So today the chemical thermodynamics completed, and from tomorrow we will start the statistical thermodynamics.